Okay, guys, in finding the area of regular polygons, we're going to pick up some new things that we haven't talked about, and I'm pretty positive that some of these things you've never heard before in any other math class. So we want to make sure that we have the vocabulary down so that as we talk about these things that you know what we're talking about. So if you'll look up here on this page, this is page 807 in your textbook. In the figure, and I rarely ever read to you, but this top section is really important, and I want to make sure you get it, okay? In the figure, a regular pentagon, that is over here, pentagon A, B, C, D, E, a regular pentagon is inscribed in circle P, and circle P is circumscribed about the pentagon. The center of the regular pentagon and the radius of the regular polygon, I should have said polygon, are also the center and the radius of the circumscribed circle. So point P is not only the center of the circle, but it's also the center of my regular polygon. Do you remember what regular polygon means? Let's just do a little review there. The regular polygon, all sides are equal, and all angles are equal. Okay, all sides are equal and all angles are equal. And if you'll remember, we had some formulas that are going to rear their heads again. Remember the n minus 2 times 180 is our sum. N minus 2 times 180 over n is the measure of one interior angle of a regular polygon. 360 is the sum of the exteriors, and 360 over n is one exterior angle of a regular polygon. So these things that we had a long time ago are still crucial that we know. Okay, now, a segment drawn from the center of a regular polygon perpendicular to a side of the polygon is called an apothem, or, if you will, I didn't want to do that, did I? Let me take that away. I meant to highlight it. There we go. Or an apothem. Different generations call it different things. The generation that I'm in, most people call it apothem, but before me, my teachers and older teachers that I've taught with in the years have called it apothem. So we're going to accept both, and I will use it interchangeably. Okay, so we have an apothem or an apothem that goes from the center, and it is perpendicular to the side of the polygon. Now that means that PF that I have up here is what we're calling the apothem or the apothem. Okay? Not only does that make 90-degree angles here, but it's also cutting our side in half. So if you'll see, by side, 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 we've created two congruent triangles in here. And that's going to help us when we find some measures. It's also important to notice that the central angle of the regular polygon has its vertex at the center of the polygon, and its sides pass through consecutive vertices of the polygon. So BPA, angle BPA, right in here, is a central angle, and to find that angle, I take the 360 degrees in the circle and I divide it by how many sides my polygon has. Since my polygon is regular, it's dividing these sides up equally. So in this particular case, since there's 360 degrees in the circle and I had that circle divided evenly 5 ways, then my interior angle up here would be 360 divided by 5, or 72 degrees. So each of these angles, right in there, right in there, and right in there, they're all 72 degrees. If I put an apothem in there, an apothem in there, I'm going to create two 36s, which tells me I'm going to have to use SOHCAHTOA sometimes. So you got to make sure you remember SOHCAHTOA. If we'll look down here at the guided practice, just to remind you, remember that this is the radius, RK is the radius of the circle, and RL is the radius of the circle. So we refer to that also as a radius of the polygon. The apothem comes from the center perpendicular to one of the sides of the polygon. It's perpendicular to the side, and it cuts the side in half. That's going to be true. To find angle KRL right in here, I would take 360 and divide it by how many pieces of a circle I have. I've got 1, 2, 3, 4, 5, 6. So I have a hexagon in there. So each central angle is 60 degrees. Now I see some 30, 60, 90 rules coming up. Okay? Up here, I have a 90-degree angle that's cut in half. So I hear some 45, 45, 90 rules. So all of those rules, right triangles, are going to come back and stay with us throughout this entire section. Now, what does this have to do with the area? Well, when we have regular polygons, and remember what our regular polygons are going to be. We have an equal, whoops, let me get my pen up here. Okay, there we go. We have an equilateral triangle is a regular polygon. Even though we have another way to find area of equilateral triangles, we can also use the formula for regular polygons. We have squares, which are regular quadrilaterals, and we know how to find the area of a square. And then we'd have pentagons that have all 5 sides equal and all 5 angles equal, and hexagons with all 6 sides equal and all 6 angles equal, and we'd have a heptagon with all 7 sides equal and all 7 angles equal, an octagon, and so forth, all 8 sides equal, all 8 angles equal. We don't have a specific formula for each of those, okay? We do for a 3-sided and a 4-sided, but we don't for these others. So all of these others have a formula, as well as the equilateral and the square can also use this formula. And that formula, the area of a regular polygon, that means all the sides have to be the same, of a regular polygon equals 1/2 the length of the apothem. Now remember, that comes from the center to the middle of a side of the polygon. 1/2 the apothem or the apothem times P, which is the perimeter of the polygon, which is easy to find. Okay, so 1/2 AP. 1/2 AP is your area for a regular polygon. Now let's see a couple. This is a good example for us to use. Find the area of each regular polygon. Round to the nearest tenth. Now the first is a regular hexagon. When I start one of these problems, like I've told you in the other problems, I always write my formula first. So since I'm finding a regular hexagon, I know that I've got to use 1/2 AP. Now the reason I do that is because that tells me what I know, and then when I plug in, and what I'm trying to find. Now with my regular hexagon, I've got, and this particular hexagon here has one side of 3. Well, since it's a regular hexagon, all sides will be 3. So 6 sides, 3 each, I already know my perimeter. My perimeter is 18. So I see that what I need to focus on is the length of my apothem right through there from B to D. All right, so to do that, what they have done from this step to this step is taken this triangle and they lifted it out over here so you could see it a little bit better. To find angle ABC, we have 360 divided by 6 sides. So that angle right there is 60 degrees, and they show us in the second picture how that 60 degrees is divided by the apothem into 2/30s. That apothem also divides my 3-meter side into two 1.5 meter sides. Now remember again, my goal is to find A. So I need to find this side. So that's my X. Okay, now I can use my 30, 60, 90 rule if I want to, or if I want to, I can use my SOHCAHTOA. I prefer the 30, 60, 90 rules simply because I think y'all need to really have those deeply embedded before I hand you over to pre-calculus next year. So with this in mind, I'm going to look at one side here, and I see that I need the long leg of a 30, 60, 90. So let me kind of shade that in a little bit. Okay, I'm just looking at it. Well, it's not wanting to help me, is it? There we go. I'm just looking at that side right there. So as I look at that side, I see that my short leg is 1.5, so the long leg has got to be 1.5 times the square root of 3. Okay, and I'm just going to, as they just put in as 1.5 on the square root of 3, and then to the last step they use the calculator, which is exactly what I would have done. This is 1.5 root 3. Then when you put the whole thing in your calculator, you see how you get an approximation to the nearest tenth, 23.4 square meters. All right, let's look at a regular polygon this time. And again, this time they've given us a little something different to look at. They've given us a different piece of given information. So I'm still finding the area of a regular pentagon. So my area is 1/2 the apothem or the apothem times the perimeter. So when I get in here, I've got 5 congruent sides, and my central angles then in here, that angle right there, RPQ, is going to be 72. So from here to here, again, they pulled out this triangle and set it up for me so it looks a little bit less intimidating. I know PR and PQ are congruent because they're both radii. And PS is my apothem, so once I find PS, I'm going to plug it in over here for A. And then, of course, my perimeter, if I find one side, if I find QR, then I'll multiply that by 5, and that will give me my perimeter. Okay, so the first thing we've got, apothem here, let's see. I've got a 36-degree angle, and I want to find PS as my apothem, so that's going to be adjacent to the 36, and 10 is the hypotenuse of the 36. So when I solve, the cosine of 36 is PS over 10, so the 10 times the cosine of 36 is my apothem. So when I put, I'm trying to see where they worked it out. Here it is. When I put 10 times the cosine of 36 into my formula, that's going to be my apothem. They didn't give me a specific number. I think I'm going to do that. 10 cosine 36. That's actually 8.09. Now that we've got that, we need to find QR down here. Well, if I can use my sine of 36 to find SR, because it's opposite 36. So the sine of 36 degrees is opposite over hypotenuse. So the sine of 36 degrees is x over 10. So 10 sine 36 equals x. But how many of those little half pieces do I have all the way around my pentagon? I've got, let me count them off in yellow. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 links that are the size of 10 sine 36. That's where this is coming from. So when I multiply 10 sine 36 times 10, I'm going to get 58.88. So if I will drop all that in my calculator and round to the nearest tenth as they asked me to, I'm going to get approximately 237.8 square inches. Okay? Now what I want you to do right now is pause the video and see what you can do with 3a. Do not use 1/2 the base times the height. I want you to use 1/2 AP to do 3a to get yourself kicked off and started in this type of thinking all by yourself. So try 3a by yourself. Take a second, and I'll come back and work it for you or with you. All right, I've got a regular polygon, and it happens to be a regular triangle. I'm going to write down the formula that I need to find that area. Since I have 3 sides that are each 4 units long, I already know that this perimeter is 3 times 4 or 12. My focus now is to find the apothem or the apothem, so I've got to find that piece. Now over here I'm going to make my triangle a little bit bigger so we can mark it up. Go in the middle. That's the piece that I need right there. That's my apothem. So let's put in 2 radii here and find the central angle. You'll usually find finding that central angle is one of the first things you're always going to do. So I have 360 degrees that I have divided up 3 ways because I have 3 sides. So I know that my central angle right in there is 120. The apothem cuts that 120 in half, so I've got a 60 and a 60. The apothem is also creates a right angle down here, so that tells me I have a 30, 60, 90 triangle. The 4 down here has been divided in half, so I have a 2 and a 2. I have the long leg of a 30, 60, 90 triangle, and I need the short leg for my apothem. So anytime that happens, I take my long leg and I divide it by the square root of 3. And that is my short leg. So over here, 2 over root 3 times 12 equals area. Now I'm just going to put this in my calculator. I'm going to have 2 divided by root 3. And I'm going to multiply that by 6 because half of 12 is 6. So I'm just going to do that step in 1. And I'm going to get 6.9 is my approximate area, and that is in square feet. Okay? Are you ready to try 3B by yourself? Try 3B. I'm going to be recharging my pencil while you do that. Okay, let's look at 3B now. Let's draw this a little larger. We have a square because it's a regular polygon. Regular polygon would have to be a square if it's a quadrilateral. The radius is 7, so I've got another radius in here, and this angle right here is going to be 360 divided by 4 since I have 4 sides. So I have a right angle. When I drop the apothem in there, it's going to divide that 90 degrees into a 45 and a 45. That's 90. So I have a 45, 45, 90, and I know the hypotenuse is 7. So if this triangle, hypotenuse is 7, I need to find a leg. So I'm going to take my 7 and divide it by root 2, and that's going to be my apothem. Okay? So my area is 1/2 the apothem times the perimeter. The apothem we just found is 7 over root 2. Now, since this particular length is 7 over root 2, this length, since I've got an isosceles triangle, is also 7 root 2. How many 7 root 2s will it take to make the perimeter of this thing? Well, here's 1, 2, 3, 4, 5, 6, 7. So I've got 8 7 root 2s will give me my perimeter. Okay, so let's see. 1/2 of 8 is 4. And then 7 times 7 is 49. Root 2 times root 2 is 2. The 2 will cancel into the 4, so I have 2 49s, which is 98 square centimeters. Okay? I think that gives you a good little push in the direction that you need to go. In this section also, we're going to talk about composite figures. So you're going to have to take figures and divide them into shapes that we've already found the area of. Okay, so like on 4A, when I look at 4A, I don't have a formula for anything that looks like that. But I could do a couple of things. The one thing that I see that I'd like to do is cut it right through here. And that gives me a trapezoid and a rectangle. And I do know how to handle those. Now, some of you are going to see it differently and want to cut right through here and have a rectangle here and a trapezoid here. That's perfectly fine. You're going to see these different ways, and that's okay. So I think with all of the problems that we've had, plus what we've gone over today, you should be pretty much set to look at some of these composite figures. Composite means you've put together a couple of different shapes. If I look at this one up here in example 4, it just caught my eye. You see how we have a rectangle, and we have a semicircle, and we have a triangle. So as you see here, you kind of have to play it out and do all of them. Again, writing down the formulas helps your focus so much. It really helps make things a lot easier for you. Don't run away from the problems because they look different. You can do this. You're smart. You can do this.